Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics. This module deals with operational amplifiers second part. Today we are going to discuss about the DC characteristics, AC characteristics, differential amplifier and its gain, and CMRR. The DC characteristics, it includes input bias current, input offset current, input offset voltage and thermal drift. When we are talking about the input bias current, we have to recall the assumptions made before analyzing the closed loop configuration of operational amplifier. What are the assumptions we have made? One is the current drawn by the input terminals, positive terminal and negative terminal of the operational amplifier is assumed to be 0, and other one, the voltage at the input terminals, the difference between the input voltage is also 0 because of the virtual ground. So, the first point, the current drawn by the input terminals of the operational amplifier is 0 ideally, but in practice, to bias the input transistors, always there will be some current drawn by the input terminals of the operational amplifier, both in positive and negative terminals. So, these current is said to be bias current, and IB plus is the current drawn by the positive terminal and IB minus is the current drawn by the negative terminal. This input bias current is calculated as the average of IB plus and IB minus, that is said to be input bias current. So, ideally the current drawn by the input terminals of the operational amplifier is called as input bias current. So, because of this input bias current, we have an output voltage in the range of millivolts or in the range of nanovolts based upon the operational amplifier made up of FET or made up of BJT. DC characteristics. The DC characteristics includes input bias current, input offset current, input offset voltage and thermal drift. What are these characteristics? So, if the input voltage is 0, we have to get the output voltage 0 ideally, but because of these characteristics, we are not getting the output voltage 0 if the input voltages are 0. So, we are going to discuss about what are these parameters and how the output voltage will be in range of nanovolts or millivolts in the case of FET op amp or BJT op amp. So, the input bias current is nothing but the current drawn by the input terminals of the operational amplifier. So, ideally we have assumed before discussing about the closed loop configuration of operational amplifier, what are the conditions we have assumed? One is the current drawn by the input terminal is 0 ideally, and another one, the voltage drop across two input terminals is also 0 because of the virtual ground. The first point, the current drawn by the input terminal is 0 ideally, but in practice there will be some current drawn by the input terminals to bias the transistors inside the operational amplifier, and these currents are IB plus and IB minus by the positive terminal and the negative terminal respectively. The average value of IB plus and IB minus is called the input bias current drawn by the positive and negative terminals, and because of this input bias current, we will be having an output voltage even though the input voltage is 0. This output voltage in the case of FET op amp, it is nanovolts, and in the case of bipolar junction transistor op amp, it is millivolts. So, this input bias current, because of this input bias current, we are getting the output voltage V0 is equal to IB plus into RF. So, this is an example of the circuit, one of the circuit getting an output voltage even though the input voltage is 0 here. So, what may be the cause of the output voltage? It is just nothing but the input bias current. The output voltage is IB minus into RF. Why IB minus? Because we are giving the input we are making the terminal negative terminal 0 here. So we are only talking about IB minus here. IB minus is the bias current drawn by the negative terminal, and see here the positive terminal is grounded. So we are considering the current drawn by this negative terminal as IB minus, and because of this current there will be some voltage drop across this resistance RF, and that is the voltage we will be seeing in the output, and it is said to be IB minus into RF. So if the resistance value is very high and the IB minus for the operational amplifier with BJT, it is nano amps, and the RF voltage is, if we select it as mega ohms, then the output voltage is 500 millivolts. So if we calculate based on this formula, the output voltage is 500 millivolts. So this 500 millivolts will cause erroneous result if we deals with the voltage in millivolts range. So we have to avoid, we have to nullify this output. How we nullify this output? By connecting a resistance in between the positive terminal and the ground, and this resistance is said to be or compensation. So this or compensation resistance across which there will be some voltage drop, that is said to be V1 because of the bias current IB plus. This V1 is going to nullify this V2 so that the output voltage will be equal to 0. So in the circuit of inverting amplifier, if we give the input signal 0, we have to get the output signal. So in that case, V0 is equal to V2 minus V1. It is based upon the KVL we have applied for the circuit. And what is this V2 is the output voltage across the resistance RF due to the IB minus current. And what is this V1? This V1 is the voltage drop across the R compensation. So by selecting the value of R compensation, this V1 will be such that it nullifies this V2, and so the output voltage is equal to 0 in the case of 0 input signal. So if you use the R compensation, we can nullify the effect of the input bias current. And what is the value of the R compensation in this case? So we have to calculate the R compensation by the parallel combination of R1 and RF. So this has to be the value of R compensation. So whatever the value we are using for R1 and RF, the R compensation will be calculated based on this. And next is input offset current. What do you mean by input offset current? It is nothing but the difference between the input bias current drawn by the positive terminal and the negative terminal. So we have assumed that the transistors used in the operational amplifier are identical and all the parameters are similar and all the parameters are balanced internally, but because of some imbalances seen practically, the IB minus and IB plus are not identical, there will be some difference. So this difference is said to be input offset current, IOS. And why this modulus value is given is maybe IB plus or IB minus is more. So the value may be plus or minus. So we got the modulus value. We don't know about which current is higher. So the difference between the bias current IB plus and IB minus gives you the input offset current. Because of this input offset current also, we will be having the output voltage RF into IOS even though the input signal is 0. So ideally, if the input signal is 0, we have to get the output 0, but even though we have compensated the input bias current, also we are having the output voltage because of this input offset current. So how we can nullify this input offset current? How we can reduce the voltage because of this input offset current? So here, if RF is very small, then this V0 can be small. But what is this RF? This is the feedback factor and this is the main part in the gain formula. So this is going to decide the amplification factor of the inverting or non-inverting terminal. So always we will be having, for example, if you take an inverting amplifier, the gain is minus RF by R1. Both are externally connected resistors. So RF is the feedback resistor and R1 is the input resistor which we have connected externally. So if this R1 is high, then the input resistance will be high. So we have to make this R1 high. If we design an R1 as 10 kilo ohms, and what must be this RF? It should not be less than R1 to have a reasonable gain. So it has to be greater than R1 because it is RF by R1. The formula is minus RF by R1. So if we have RF high, then only we will get a reasonable gain for the amplifier. In the case of non-inverting amplifier also, the gain formula is 1 plus RF by R1. Here also, if R1 is 10 kilo ohms, at least this RF must be greater than this R1, maybe 5 times or 10 times according to the design. So we cannot make this RF small. So what we have to do for compensating the effect made by the input offset current? For that, we are designing a circuit. In the feedback path, it is a T feedback network. In this circuit, it is a T feedback network provided by R2, RB and RA. This T feedback network gives high resistance to the inverting input terminal. So in the case of the amplifier circuit, we can use this T network, and if you want to deal with the very smaller range of input signal, so we have to convert this T to pi, and if it is in pi connection, then the resistance in the feedback network is very low. So based upon the application, whether it is going to be an inverting amplifier with a higher range of signals, you can have this T network as such. And if you are going to deal with very smaller range of input signal, then you have to compensate this input offset current by having a pi configuration here instead of T. So we have to convert this T feedback network into pi. So for which you have to know the formula to how to convert the T network to the pi network. And this is a good solution to nullify the effect made by the input offset current. And now, even though you have compensated or reduced the effect made by the input offset current as well as the effect made by the input bias current, still there will be an output signal if the signal at the input is 0 by the factor called input offset voltage. What do you mean by input offset voltage? So because of the mismatch of the transistors internally, we are getting an imbalances in the circuit by which we are getting an output voltage. This is said to be an output offset voltage. To nullify this effect, we have to give some input voltage called input offset voltage to nullify the output voltage when the input signals are 0. So how will you give this input offset voltage to nullify the output offset voltage? So we have to recall the pin configuration of IC 741. We know that the pin number 2 and 3 is for inverting input and non-inverting input, and 6 is for output, 7 and 4 is for positive supply and negative supply respectively, and this is for 1 and 5 is for offset null pin. So what is the use of this offset null pin? So across these two pins, we have to connect a potentiometer, and a wiper is connected to the negative terminal or a positive terminal, so that we can give either a positive voltage to the input terminals or the negative voltage to the input offset null, so that the output voltage will be nullified. So across this first and fifth pin, here if you see this circuit, 10 kilo ohm potentiometer is connected across these two pins 1 and 5. It is not mentioned in the circuit here. Across this 1 and 5, we are connecting a potentiometer, and a wiper is connected to the negative supply of the circuit. So if you change the position of the wiper, accordingly the voltage applied to the first and fourth pin, and this voltage is going to nullify the output if the input signals are 0. So we have nullified the effect made by the input bias current, input offset current, output offset voltage. Still there will be some output even though the input signal is 0. We will have a break now. Welcome back. So we have discussed about the input bias current, offset current and output offset voltage. For these parameters we have a compensating techniques also discussed. Even though we have given all the compensation techniques to nullify the output if the input are 0, again there will be some output voltage because of the thermal drift. If a circuit is perfectly designed at the temperature 25 degree centigrade, this may not work for the temperature 35 or so, 35 degree centigrade. Because of the change in the temperature, again we will be having an output voltage because of all these parameters. We can say that offset current drift is expressed in nanoamps per degree centigrade and offset voltage drift is expressed in milliamps per degree centigrade. So for every increase or decrease in temperature in per degree centigrade, there will be 1 nanoamps or 1 milliamps change in the offset current and offset voltage. So for which we have to design the PCB very carefully to keep away the op amps from the heat source, and forced air cooling may also be used to stabilize the ambient temperature. And these are all about the DC characteristics of operational amplifier. So what are the DC characteristics of operational amplifier? It is input bias current, input offset current, input offset voltage and the thermal drift, for which we have discussed all the compensation techniques. And now we are going to see about the AC characteristics of operational amplifier. So in order to have, what are the AC characteristics of operational amplifier? Frequency response of an operational amplifier and slew rate, and also stability of an operational amplifier for the lower range of frequency to higher range of frequency. Slew rate will be discussed in the later slide, and now we will see the frequency response and stability factor. So frequency response of an operational amplifier. What is a frequency response? So what is the response of the operational amplifier for lower range of signals to higher range of signals? This is said to be frequency response of any circuit. If the gain of the operational amplifier, say for example 90 dB at 0 frequency, 0 hertz of frequency, the same 90 dB gain must be maintained for higher frequency ranges, but it is not so in practical. What is the cause of the decrease in the gain for the higher range of frequency? This is because of a capacitance effect present in the circuit, inside or externally. Internally or externally, there may be a capacitance effect in the circuit. What causes this capacitance circuit? Because of the physical characteristics or the internal construction of this operational amplifier. Maybe because of these reasons, there will be many number of capacitance effect seen in the circuit. So each capacitance effect will produce minus 20 dB per decade roll-off rate in the gain of the operational amplifier. So about this frequency response, when we see this capacitance, if we consider the capacitance effect as 3, or if we consider the capacitance effect as 1, the roll-off rate is minus 20 dB per decade, and if it is considered to be 3, then the roll-off rate is minus 60 dB per decade when you increase the frequency. What do you mean by dB per decade? What do you mean by minus 20 dB per decade? So for every decade of frequency or every 10 times increase in frequency, the gain is reduced at the rate of minus 20 dB. This is said to be dB per decade, right? Or it can also be called as 6 dB per octave. For every octave, for every increase in octave frequency, there will be the roll-off rate as minus 6 dB. So you can say it as minus 20 dB per decade or minus 60 dB per octave. And next is the stability of an operational amplifier. The closed loop transfer function can be written as ACL is equal to A by 1 plus A beta. What do you mean by ACL? It is closed loop gain, and A is open loop gain, and beta is feedback factor. If the characteristic equation 1 plus A beta is equal to 0, the circuit will become just unstable. This leads to sustained oscillations. What is the condition for oscillation is magnitude of A beta is equal to 1 and phase angle is 0 or multiple of 2 pi. So, if the circuit satisfies these two conditions, then the circuit will become an oscillator. It just starts its oscillation, or the circuit is unstable when this will happen. If the circuit contains a capacitance effect, because of this capacitance effect, the single capacitance effect will produce minus 90 degree phase shift, or if we see any 3 capacitance effect, then the phase shift is minus 270 degree. And if the inverting amplifier is considered, the amplifier itself produces 180 degree phase shift. So, if any 2 capacitance present in the internal circuit, then this capacitance effect will give you minus 180 degree phase shift. So, in total the phase shift is 0 or 360 degree. So, this is one of the condition for oscillation. And if the closed loop gain is greater than the open loop gain, or AB is negative, by this characteristic equation we can say that 1 plus AB is equal to 0, then A beta is equal to minus 1. If it is negative, then as per the formula ACL is equal to A by 1 plus A beta. If this is negative, then ACL is higher. ACL is higher than A, that is the closed loop gain is higher than the open loop gain. This leads to unstable circuit. So, at one point this A beta is equal to minus 1, and because of the capacitance effect we know that the total phase shift becomes 0 or 360 degree. So, both the conditions are satisfied, then the circuit will become unstable. So, we have to carefully design the circuit, and we have to have a greater bandwidth and lower closed loop gain in the AC characteristics of the operational amplifier, for which there are compensation techniques, frequency compensation techniques called externally compensation technique and internally compensation technique. In external compensation technique, we have again two types: dominant pole compensation and pole zero compensation. So, in dominant pole compensation, externally we have to connect a resistor and a capacitor by which a dominant pole is introduced in the transfer function, by which we can have a frequency F1. So, already if the 3 capacitances are considered to be in the circuit, then we will be having 3 corner frequencies F1, F2 and F3, and we can say that F1 is less than 0 and F2 is less than F1 and F3 is less than F2. So, if you introduce a pole, dominant pole in the circuit, and in the frequency response of the circuit, the first corner frequency, the gain of the operational amplifier touches the 0 dB line at this pole which we have introduced externally. So, what is the roll off rate at that point? Consider this is the frequency response of the operational amplifier, and this is a constant gain, and here say this is F1, which is the pole introduced in the circuit by connecting externally the capacitor and a resistor. So, these are the corner frequencies already have in the circuit, and this is the gain in dB, and this is the frequency. So, here what is the roll off rate? It is minus 20 dB per decade. So, here this open loop gain which touches the 0 dB line at the frequency called F1, which is the pole we have introduced in the circuit by externally connecting a resistor and a capacitor to the operational amplifier. So, here the roll off rate is just minus 20 dB per decade instead of minus 40 and minus 60 dB at this F3. If there is no compensation, then the frequency response will be like, it is constant for the lower frequency and it decreases at the rate of minus 20 dB per decade up to F1, and again it decreases at the rate of another minus 20 dB per decade. So, it is totally minus 40, and this is at F2, and again it decreases minus 60 dB per decade at F3. So, these are the frequencies produced by the internal capacitance effect. So, this is without a compensation technique and this is with the compensation technique. So, without compensation technique the roll off rate is minus 60 dB per decade, and with compensation technique the roll off rate is minus 20 dB per decade. So, the roll off is only 20 dB per decade here. So, this is about the dominant pole compensation, and next is pole 0 compensation. Why we are going for pole 0 compensation is, in the dominant pole the bandwidth is reduced here. The dominant pole, the bandwidth of the circuit is reduced, and one advantage of the dominant pole is, if the bandwidth is reduced, it becomes a noise immune system. Where will you get a noise? Only at the higher frequency range of signals. So, if we eliminate these high frequencies, then noise will also get eliminated. So, it is a immune noise system, and disadvantages are reduced bandwidth and reduced slew rate. So, we are going for pole 0 compensation. Let us summarize this session. So, we have seen the DC characteristics includes bias current, offset voltage and thermal drift, and how the effect of these DC characteristics can be nullified also, and what are the AC characteristics, frequency response, stability, and the frequency in frequency response, the compensation techniques. One of the compensation techniques we have discussed, it is dominant pole compensation. Let us check how you have understand the topics. So, what is bias current? What is the use of the offset null pins in IC 741, and what is the output offset voltage? These are the references. With this we have come to the end of the lecture. Thank you.